class, Sam and Michael here are worried that you're not getting enough experience with caddis.
Yeah.
So they have an offer for you.
Yeah, I don't know how many of you, I see some familiar faces, have heard about the Competitive Coding Club. Basically, we run this programming contest club, similar to the caddis problems you do. And basically, every other week, on a Tuesday at 5:15 in MEB, we run a little programming contest. And it's like a great way to get more experience with like interview problems and more of this kind of stuff if you're really into it. Yeah, and also like if you're interested, we're also advertising something called Google Games, which is an event that's happening on the 21st, and it's teams of 4 to 5, and I think it's going to be like a programming contest as well. So if you're interested, we have a mailing list, so just go to that URL, and then you can fill out your information. And I think later today we'll be sending out more details about our future meetings as well as Google Games.
Yeah, we're planning on sending an email around about like 3 today.
Thanks.
Thank you. Okay. Any questions or problems? This week assignment coming okay? Yes? Okay, so I've talked to a lot of people about decision trees for merge sort. Here's the common misconception I found. Instead of a decision tree, folks want to draw recursion trees. Okay? So a recursion tree traces out the sequence of recursive calls that are made by merge sort. What does a decision tree contain? What are the nodes of a decision tree? They're comparisons. A decision tree is a tree of comparisons made by merge sort. A path in the decision tree shows you a particular sequence of comparisons that merge sort will make in getting from completely unsorted to sorted. So the root node of a decision tree for merge sort is the first comparison that merge sort makes. So at what level of recursion is that first comparison made? What did you say? It's made somewhere deep down in the recursion tree when it's getting ready to merge two-element array. Okay? So it's completely different from a recursion tree. Any other questions? Yes?
I'm confused by that. The first comparison is if the size is greater than 1, and so doesn't that get made?
Now, okay, when we talk comparisons in a sorting algorithm, what kinds of comparisons do we mean?
Comparisons.
Yeah?
Comparisons that result in a branch in execution? Like a fork in, like a decision.
Okay. Yes?
You're comparing two elements.
Comparing two array elements, not comparing an array index, you know, your index. So,
Oh, yeah.
let me save this here and I'll call it. For example, let's say we're sorting the array A, B, C, D using merge sort. What's the first, what's the first comparison merge sort makes?
It's already sorted.
Well, we don't know. A, B, C, D are variables. They just stand for arbitrary numbers. We don't know whether it's sorted or not. Okay? So, you know, I'll draw the recursion tree here. You know, it will recursively sort this subarray and recursively sort this subarray. And then it will make a call to sort that. So actually this part over here wouldn't have even been generated yet, so let me take that out. Okay, so we get to this point. It still has not compared array elements. Okay, this is the base case. So it just returns. Then it'll make a recursive call to sort that array. That's the base case, so it returns. Okay, and now it's got to essentially, it's got to merge this half of the array with that half of the array. Finally, it does a comparison. It compares A to B. So the first comparison that happened was comparing A to B. So at the root of your decision tree over here is the question, is A less than B? And the answer is either no or it's yes. So decision tree is just keeping track of what comparison, or it's showing you all possible comparisons that could happen depending on what paths, whether the comparisons are yes or no. All right, so the answer is no or yes. What's the next comparison that's going to happen if the answer was no here? No, the algorithm's not done. Okay, so who can tell me what happens next? Yeah.
Is C less than D?
Okay, the next comparison is going to be if C is less than D because, okay, it'll merge these two things here as either A, B, or BA depending on the comparison. Then we'll return, another recursive call is made, another recursive call is made which returns immediately, another one which returns immediately, and now we have to merge the first half of this, the second half of that, and so it'll ask, is C less than D?
It's the same for the yes case.
Now, it didn't matter what the yes case was. I mean, it didn't matter if it's yes or no, you're going to do the same comparison in these in. Okay? And each of those could be no or yes. And the next comparison that happens will be at this level of the recursion, when it tries to merge the first half with the second half. But whether this is A, B, or BA here, or whether this is C, D, or DC, depends on what the answers to the questions down here were. So let's just say if A was less than B and C is less and C was less than D, what will be the next comparison?
Is A less than C?
Yes.
Is A less than C?
Right. Is A less than C? Because the merge would have left AB alone and the merge would have left CD alone. And so we're asking if A is less than C as part of the merge operation. So all the comparisons happen in the merge.
Is this without the optimization?
What's that? This was without the optimization. Okay? So you got to understand the merge operation, essentially. I will tell you, though, that if you're drawing out the entire decision tree for a 4-element merge sort, you're wasting your time. You just need to understand what the tree is, be able to think about the tree. You can do that without actually drawing the whole thing once you get the idea. And you know, because eventually you got to solve the problem for an arbitrary array. You're not going to be drawing out decision trees for arbitrary arrays. Any other questions? Yes?
So back on DAGs and linearization, is it, okay, so if you call explore on a vertice, and all those nodes that have been visited from that one explorer, and then we take those vertices and extract them in order from our linearization, is that I don't know, is that guaranteed to, like... Okay,
so let me interrupt you. So you're talking about explore, you're talking about linearization.
Yeah, I'm trying to get the, so I do the topological sort
On
the whole graph.
On the whole graph, yeah.
But then for autosync, I need to only extract out the part of that linearization.
No, okay, so you're talking about autosync?
Yeah.
No. You don't have to extract anything out for autosync. You just linearize the graph and then process the vertices in order.
What about if we? But there are nodes that we don't care about, though.
Well, there are various ways to deal with that. Let's go back and see if I can. I've saved all these things. If I can go back to the old one. I have an open file. Copying it. Oh well, I'll just redo it again. Okay, let's suppose you're doing autosync and you have this vertex here and this vertex here, and you got C, and then you've got various ways to go. And let's say you're interested in the cheapest way to get from C to F. Right? And there's various entry fees. There's a $5 fee there, a $2, a $3, a $10, a $20, $1, and an $8. So if we topologically sort it, what do we get? We're going to get A, B in some order, and then C, and then D, E in some order, and then F and G. So alphabetical order in this case happens to be a topological sort. Okay? Now, what he's worried about is you've sorted it, but he's saying we don't really care about A and B. If we're only interested in the cost of getting from C to F, we don't care about A and B, so he's wanting to extract out a piece of the graph and ignore the rest. I'm saying you don't need to do that. Okay? Let's just process the vertices in order. What's the, if you're a leaf node, I'm sorry, a source such as A and B, okay, what number are we trying to calculate? What number do we want to associate with each vertex here?
The cost.
Well, not, yeah.
The lowest cost of traveling to that?
The lowest cost of getting to that thing from C. Right, we're trying to calculate the lowest cost to get from X to, from C to X for each X. And eventually when we calculate it for F, we'll have our answer. Okay? So what's the cheapest cost of getting from C to a sink? To a source node? Right? Unless C is the source node, it's infinite. You can't get from any vertex to a source unless that vertex is the source. So the cost of these are infinite. Now, no matter where C is, what's the cost of getting from it to C? From C to it. 0. So essentially, you process these things in order. You process A by saying, okay, it's a source. It's not C, so the cost is infinite. You can't get from C to it. You process B. You say, it's a source. Can't get, and it's not C. I can't get there from it. Right? Next thing you want to process is C, and there's a special case because that's the thing you're starting from. So what cost does it get? You just look at the predecessors, find which one is the cheapest, and add 10 to it. So we only have this one predecessor here. It costs $0, and so we add that to 10, and we get $10 here. Yeah?
That finding which one is cheapest,
Mm-hmm.
a lot of people are using Dijkstra's algorithm for that. Like, is there...
Well, if you want to use...
Like,
Dijkstra's algorithm is overkill for this.
yeah, that's what I was thinking. I was wondering, like, I'm assuming there's an easier way. I'm just trying to...
Yeah. This is the easier way. Linearize the graph, apply a simple computation at each vertex. Yeah?
Is there something that happens, okay, so passing like the first 5 tests, is there something that happens after the 6th test?
No. Nothing special happens. They just get longer. Let's finish the example here. You've dealt with D. With E, you've got one predecessor. It costs $0 to get there from C, and so you add the $20. Finally, you get down to F. There's 2 predecessors, $10 and $20. So this becomes 11. At that point, you could quit once you found the F. But you kept going, you'd find out that this one down here is $19. So you don't really have to extract the vertices you care about. You just compute for all of them. Yeah?
We're doing a lot of extra work we don't need to when we hop over all of these nodes.
Yeah, you could find, if you want to, you could make it more efficient by not dealing with these. Just starting right here. And then if you encounter a vertex that you depend on that doesn't have a cost, you treat it as infinite. There are always tricks to make things faster. We'll see. We'll talk about shortest path algorithms. Dijkstra's is a fine algorithm, but there's a better algorithm for DAGs, and this is it. Yeah?
A question about adjacency lists.
Uh-huh.
So when we're doing that quiz, are we operating under the assumption that those linked lists that are stored in each of the vertices is the lookup a
A
constant?
list determines the size. I said, in the problem, I said, don't assume the size is stored.
Okay, well,
Explicit.
it says don't assume that you know the number of edges, so I didn't know if that meant for like,
No, I said it was more specific. It says, don't assume that you know the number of edges out of each vertex.
okay.
That's not stored explicitly with each list. But keep in mind, if you want to know, are there at least 2 elements? Suppose you want to know if there are at least 2 edges out of this vertex. You don't need to look at the whole list to decide that, right? You just need to go at least this far to decide there's at least 2. You don't have to go all the way to the end and then say there are at least 2. If you want to know whether there's an edge or not, any edges, you just have to look and see if there's a null right there. Any other questions? Okay. Let us go.
Actually, I do have a question.
Yeah, go ahead.
After you use depth first search and assign post and free numbers, you want to sort the post numbers in descending order to get them.
Yeah, topological sort in sorted order. And you don't really have to do a sort. I showed you how, just as you find post numbers, you can just put the element into the sorted array. First element you find will have the lowest post number, so you put it at the end of the array. The next one will have the next lowest, so you stick it next to the end of the array. So you can fill in the array as you do the search. Yeah?
I haven't thought this through completely, but I was thinking about it on the way in class. So there's a correlation between the post numbers and topological sort.
Yeah.
Or in reverse topological sort, is there a correlation between?
It's just the opposite.
But I mean, as you're going through and you're getting the post number.
If you want to reverse sort it, when you find the first thing with a post number, you just stick it at the beginning of the array.
Okay.
And then fill it in that direction.
That makes sense.
So I mean, if you're calling a sort algorithm in your autosync, you're working too hard. Okay, so we've been talking about depth first search for a while. We never got around to analyzing it, so let's do that. So there's our algorithm. We have depth first search, and remember it marks everything in the visit array, it fills out the visit array, and then it iterates through the vertices, and it finds an unvisited one it calls explore. And then explore marks something as visited, pre-visits, and then for each edge out of the vertex we're looking at, it possibly explores it if it hasn't been visited, then it post-visits. So this is going to be a little tricky to analyze. What? What is tricky about this? Well, it's not straightforward. Yeah.
We don't necessarily know the big O of pre-visit and post-visit. They could be doing anything.
Okay. So he said we don't know the complexity of pre-visit and post-visit, so let's just call that constant. We won't worry about that. Okay? That's one thing out of the way. What else is going to make it hard? Yeah?
We have a recursive call, but we don't know the size.
Right.
The problem that we're recursively calling on.
We keep making we make this recursive call up here. But you make any particular recursive call, how complex will that be? It might bottom out right away. Or it might do a whole lot of work. Furthermore, how many times do we call explore from DFS? Once for each chunk. It might call it once, it might call it V times. We don't know. So we have to be careful. If we assume that every time we call explore, we'll get the worst case. If we assume every time we call explore, it will explore all the vertices, we're going to end up with an overestimate. So we'll have to be a little bit careful. You'll see what I mean in a second. So first thing we have to do is initialize the visited array. Right? That's easy to see. That's O of V. by that. Time is proportional to the size of the array we're initializing. And then think about that for each loop right there. Okay, I don't know how complex the body of the loop is, but the cost of iterating through the available vertices, that takes linear time, just enumerating the vertices. And that checking, together with checking the visited array, that's going to be done once for each vertex. It's the explore part I don't know about. So we got O of V for the for each vertex, if not visited part. Then I haven't counted for the explorer. Okay. So now let's think about, we've dealt with part of DFS. So let's think about over the life of one call to DFS. And so I claim that I don't know how many times Explorer is going to be called, but I know that this statement right here is going to be executed V times. Okay. Why is that true? I don't mean it's executed over the life of the entire algorithm. This statement is going to be executed V times. Yeah.
We are going to check each vertex, and we're only going to set it to true once.
Right. When Explorer is called, Explorers end up being called once per vertex. And so when it's called on V, this will be set. And once we've set it, we'll never call Explorer on that vertex again, because these conditionals here will stop it. So whether DFS calls Explorer once, or DFS calls Explorer 3 times, or DFS calls Explorer V times, we don't know. But over the life of the entire algorithm, we'll hit this statement V times. Okay, so the cost of that set, that is V times. What about pre-visit? How many times do we call pre-visit? Over the life of the entire algorithm, V times, once per vertex. Okay, now we get down to here. So let's break this down into its pieces. We've got to find all the edges out of V. And once we find the edges, we execute this stuff in here. So over the cost of the entire algorithm, now we're not talking about a single call to Explorer. How much work are we going to do over the course of the entire algorithm enumerating edges? You said O of E. And you say? V plus E. Okay, anyone else have any thoughts on it? Yeah?
O of V plus O of E.
He says O of V plus O of E. Yes?
E times V.
E times V. Okay. Well, what does it take to essentially enumerate all the edges eventually? Each time to explore, you'll enumerate some of the edges, but over the life of the entire algorithm, you find all the edges. What's happening? What's happening when we're finding these edges? How do we find the edges?
Exploring.
No, we don't call explore to find the edges. Where do we look for the edges? Yeah?
Adjacency list?
He said the adjacency list. That's one possibility. What's the other possibility?
Adjacency matrix.
It may be an adjacency matrix. The bottom line is to find all the edges in the graph, you've got to look at the entire data structure that's representing the graph. You've either got to look at every bit of the adjacency matrix, or you've got to look at every bit of the adjacency list. So the time it takes to find all the edges over the entire course of the algorithm is the size of the representation. So if we're working with a list, it's going to be O of E plus V, because that's how big that is. If it's a matrix, it'll be O of V squared. Now, in an individual call, so you're finding the edges out of a specific vertex. If you're using a matrix, what's the cost of a single finding all the edges out of V?
O of V.
That's O of V. You just go down a row. So that would be easy to deal with. Every time you call explore, there's an O of V calls to find the edges out, if you're using a matrix. What about if you're using adjacency list? You've got to go into the list to V's list. You go into the array, find V's list, and then you got to look at all the things in that list. So the complexity is the length of that list. Well, how long is that list? It could be as long as V. It could be as short as 0. We don't know how long it is, but we don't have to know, we don't really care because we're trying to find the complexity over the entire life of the algorithm. So some calls to explore won't have to work very hard to find all the edges out of a vertex. Others might have to work harder, but it'll add up to V plus E. So it just depends. So we'll just put that as a placeholder. The cost is going to be whatever it costs. Depends on the representation. All right? We call visited. How many times are we going to call? How many times are we going to check the visited array over the life of the entire algorithm? No, so just exactly how many times are we going to call it? Don't need a big O. Yeah? E times. What's your reasoning?
It seems to make me need to check every edge to know if the distance is
Yeah, once per edge. Every time we find an edge, we see if its endpoint has been visited. We find an edge from V to U, we see if its endpoint's been visited. So over the entire life of the algorithm, we'll identify all the edges and see if the endpoint has been visited. So that's O of E. Okay? Okay? And then how many times will we actually just go through the overhead of making a method call to explore? I'm not asking for the complexity of explore. I'm just the complexity of pushing a stack frame and doing, initiating the recursion, and then later popping the stack frame. How many times do we call explore? Yeah?
We call explore once for each vertex.
Once for a vertex. And so that's why the overhead of that is O of V, once per vertex, or V vertices. And finally, we call post-visit V times, and we're assuming that's constant. So that's it. Some of the things we can account for explicitly just, because they happened before that loop started up in DFS. The stuff that happens inside the loop and inside the explore method, we accounted for that by not asking how much does it cost each time. We ask how much does it cost over the entire life of the algorithm. So we just have to add it all up. And what we get is, it's O of V. There's some O of V terms. There's some O of E terms. And there's the cost of enumerating the edges. And for a matrix, that turns into O of V plus O of E plus O of V squared. That's the dominant term. So it's O of V squared. And for a list, it simplifies to O of V plus E. That's the complexity of depth first search. Yes?
What's enumeration?
Enumerating the edges. Right. Cost of finding all the edges. Yeah?
Why isn't that captured in just the O and E term? Yeah.
Why is what?
Enumeration.
Okay. He's asking why, if we're enumerating an adjacency list, why isn't the cost O of E? You say you don't know the number of edges. You could have a data structure. Imagine an empty graph. What would be the cost of enumerating all the edges in an empty graph? Yeah? It'd be V. You'd have to go down that array and notice, oh, there's nothing here, there's nothing here, there's nothing here. Even though there are no edges, you've at least got to walk down the entire array. Similarly, you could have no edges and you're using adjacency matrix representation. It'd still take V squared time to find out there are no edges. You've got to consume the entire data structure. So, could we improve? Is there like a better depth first search out there that we could make our name on? Yeah?
No, because we have to consume the entire...
Right. You said you have to consume the entire data structure. If the data structure is V squared big, just what it is. You've got to at least look at the entire data structure. And similarly here. So to have a better DFS, you have to have, I guess, a smaller data structure or something. But if you're talking about lists and matrices, that's the best you can do. Yeah?
Just out of curiosity, is there a way to do it in sort of parallel compute, at the same time?
To do it in parallel? Yeah, I mean, you can always consider parallel algorithms. This one, I'd have to think pretty hard about. I mean, there's... Yeah, I won't speculate right now. Any other questions? Okay, so there's an analysis of the algorithm. And what makes it a little more difficult than what we're used to is there were two variables, V and E, that we have to consider. And then there's sort of, we couldn't analyze the complexity of a single call to explore. We sort of had to analyze the cost, overall cost to explore they're going to have. Some of them are made from up there, some of them are made from down here. All right, now I'm going to show you one more application of DFS. And that is strongly, this is an algorithm I'm going to show you for detecting the strongly connected components of a directed graph. Okay, there's a parallel notion that we talked about briefly with unconnected graphs. And that's the connected components of an undirected graph. So what are the connected components of an undirected graph? What does that sound like to you? Yeah?
Wherever you can get throughout the graph.
You said wherever you can get throughout the graph.
So if you have two connected parts, you can start here. If you get to all the other nodes, and start here, you can only get to these.
Okay, so essentially think about the way depth first search works in an undirected graph. You start anywhere, you start at some vertex, and you explore until you can't get anywhere else. So that chunk you just explored is called a connected component. From any vertex in the connected component, you can get to any other vertex. But a graph might have multiple connected components if there's not edges in between the chunks. So it's just how many chunks there are. The issue becomes a little more subtle in a directed graph. Because just because there's an edge from A to B, you wouldn't say A and B are connected in some sense, because you can't get from B to A. The edge is a direction. So for the definition of a strongly connected component, we're going to say that two vertices of a directed graph are connected if there's a path from U to V and from V to U. So are B and E connected?
Yes.
Yeah, you can get from one to the other. What about H and I? Are they connected?
Yeah.
Yes.
Yeah, you can get from H to I to H. What about F and H? Are they connected?
No.
You get from F to H, but there's no way back. Okay? So that's what it means for two vertices to be connected. So what we say now is that what we form are the largest possible chunks in which every vertex is connected to every other vertex. And that is what we call a strongly connected component. So we don't want to just say that H and I are strongly connected. We want to clump it with everything that's mutually strongly connected. So what are the strongly connected components of this graph? You can always decompose a directed graph into a strongly connected. Yep.
B and E, C and F.
Okay, so
H.
stop there. B and E, he said, and C and F. Okay, who could tell me some more chunks? Yeah?
Everything beneath E and F.
Right, this mess right here is all strongly connected because there's you can see that everything's reachable from everything else. Okay, someone else. What's another strongly connected component? You got to be able to put, you can divide the graph, you got to account for every vertex. Yeah?
Account for every vertex?
Yeah.
Oh, E. Sorry, A.
A all by itself constitutes a strongly connected component. We assume you can get to a vertex from itself. And so does D. Okay? So there they are. So there are 5 strongly connected components. All right? Now what if we computed the strongly connected components of a DAG? That's a directed graph. We could compute its strongly connected components. What would they be? Yeah?
The vertices.
Just each vertex would be onto its own, an SCC of its own, because there's never a way to, if you can get from one vertex to another, there's no way to get back, because it's a DAG by definition. Okay, so the algorithm isn't interesting when you run it on DAGs. Now look what I'm about to do. I'm going to remove the internal structure of these SCCs. I'm just going to remove the edges. Okay? So I just remove the edges, and I rename the vertices. Now the dotted things are the vertices. And that's almost a directed graph. Why is that not quite a directed graph? Yeah?
There's two edges from BE to CF.
Right, there's two edges from BE to CF, so we get rid of one of them. And what's left is what? When you do this transformation I just did, what kind of directed graph do you end up with? It's acyclic. It's a DAG. It has to be, because what if it weren't? What contradiction would that lead to if it turned out this thing wasn't a DAG? Yeah?
If there was a cycle between any of these, then they would all be part of one strongly connected component.
Right. Like if there were a cycle between BE and CF, they should have been the same strongly connected component in the first place. So, what this is called is the metagraph. So when you run the strongly connected component algorithm and find the strongly connected components, what you can create is a metagraph, which is a DAG. So these things we'll call metavertices. The whole thing is a metagraph. We'll look at some applications of this later. But the crucial thing to remember, well, I'll give you a preview. The reason you run a strongly connected component is sometimes you want to solve problems on a directed graph, and it turns out you can break it into steps. You can, what you do is you convert it to the metagraph. You solve the problem on each metavertex, and then you solve it on the entire graph by applying a DAG algorithm. The DAG algorithms are easier to use. Okay? So sometimes it's advantageous to simplify the graph into its strongly connected components because they're easier to deal with. All right. Well, let's see if we can sneak up on an algorithm for identifying strongly connected components. All right. Here's a statement. See if you believe it. If we start exploring a vertex that belongs to a sink in the metagraph. Now, the metagraph isn't shown here. Remember what it is. But if you start at a vertex that would be part of a sink of the metagraph, I claim it will visit all the vertices in that sink and then stop. Why does that make sense? So this is a D up here is a sink in the metagraph. If we start exploring from D, we'll visit every vertex in that sink, in that meta vertex and stop. I mean, that's obvious. You start at D, you're not going anywhere. What's the other sink in our metagraph? This chunk at the bottom. And what if we just started searching at J? Would we touch any vertex outside of the meta vertex? No. You're sort of stuck. Okay. So that's an interesting observation. So let's look. We start with G here. You know, we just do the depth first search. And we're done. Nowhere else to go. We've identified we have stayed inside the meta vertex. Okay, now, how could this turn into an algorithm for identifying strongly connected components? Let's say we had an oracle that would tell us a vertex in this graph that actually occurs in a sink of the metagraph. How could we use that information to peel off the strongly connected components? Yeah?
Could you just remove all of those vertices from the graph altogether and then you'll have new sinks?
Exactly. We've identified this chunk. That's a meta vertex. Take it out of the graph. Now do another explore starting in a sink of the new graph. So maybe our oracle would say, okay, now start at D. And we'd find D's a meta vertex. Take it out. Then it says, okay, now start at F. And it would find CF. You pull that out. And our oracle would say, start at B. And we find BE. And then it says, start at A, and we find A. So if only we had this oracle that would tell us where to start, we'd be good. So that's what we're looking for, is a way to implement this oracle. So the question is, how do we find a vertex that's in a metasync? And how do we continue after we discover the metasync? Well, I just told you how we continue after we discover the metasync. You take it out of consideration and restart explore somewhere else. So the crucial question is this one right here. Yeah?
So just look for the back edges, right? And that would give you
Well, you say looking for back edges. We'll see what the algorithm is like. It's not that simple. Yeah?
I think if we topologically sorted the metagraph, then at the back, or say reverse order, you'd start with sinks and then work your way up to sources.
Right. Well, you're saying if we topologically sorted the metagraph, it would tell us, we'd be able to tell which vertices occurred in the metagraph. The problem is, we're trying to find a way to get the metagraph. All right. So we can't assume we know the metagraph. Yeah.
Explore one of the vertices and keep track of the lowest post number that created a cycle.
Okay.
Or no, lowest pre-number, sorry.
Okay. So various ideas. It's easy to come up with wrong ideas. I mean, I'm not going to say your idea is wrong. But
It probably is.
You've got to think about it harder than you're going to get a chance to here. With graph examples. But you're on the right track. It has to do with pre and post numbers. So let's see. Okay, let's see what this says here. If x and x prime are strongly connected components, and there is a path from a vertex in x to a vertex in x prime, then the highest post time in x is bigger than the highest post time in x prime. Well, that's a mouthful. But let's just see what I'm talking about. So let's do a depth first search that starts at C. Okay? So we're going to start at C. Then, it explores all around. All right? So at that point, think of X as being CF. We happen to know that CF is a strongly connected component, and so is this. And what that says up there is the highest post time in X is bigger than the highest post time in X prime. Is that true? The highest post time in X is 16, and that's bigger than any post time down here. Okay? Now, you may say, well, sure, you started searching in X. Okay, suppose we started the depth first search at I. What would have happened? Yeah?
You wouldn't have ever reached CNF.
Well, all of these would have gotten post times.
Right.
And then, remember, we're doing a depth first search. So if we started here, we would get these all post times. Then we restart the search somewhere else. Eventually, those guys would get post times. They'd have to be bigger because they came after this. So let's do it. Let's restart at D. It gets a 17 and an 18. Then let's go to A, and it gets 19, 20, 21, 22, 23, 24. And so what you see is that, A has the highest of all, right? There's a path from A to every other vertex. A is a strongly connected component, and so that component has the highest post time of all. The highest post time in this chunk is less than the highest post time in the BE chunk, the CF chunk, and the A chunk. So what does this suggest? Remember, our problem was to try to find, if we could, given a graph, if we could identify a vertex that's in a metasync, we're pretty sure we could find strongly connected components. Yes?
Do you maybe order it by like the highest post number in like a...
Okay, so clearly highest post number is important. Yeah. Yeah?
Reverse the graph?
Okay. So what she's observed, I'm assuming, is that what we have found here is not, we don't have a way to find a vertex in a metasync. What have we found here? If we do a depth first search on a graph, what can we find? We can identify a vertex that has to be in a meta source. And what is that way? How do we, by doing a depth first search on a graph, how can you find a vertex that will eventually end up in a meta source? That is part of a meta source in the meta graph, even though we don't know what the graph is. How do we tell? Yeah?
Highest post time.
The highest post time. No matter how you do the graph, there could be more than one meta source, but the highest post time has to belong to a vertex that goes into a meta source. And so, what does reversing the graph have to do with it? Right. We want to have a way to find meta sinks. We just found a way to find meta sources. So we just reverse the graph, do the depth first search. It'll tell us where a meta source is in the reversed graph. But that's a sink in the original graph. So imagine if we flipped all the arrows and found out that this thing here, that say K ended up with the highest post time. That would tell us that K is part of a meta source in the reverse graph, but it means it's in a meta sink of the original graph. So that's the key idea. And this is what we just talked about. So the highest post time belongs to a vertex in a meta source. And if we peel that off, where's the new highest vertex? The new highest post time? It belongs to B. Is that a meta source of the reduced graph?
Yeah. Well, it's part of the meta source.
Yeah, B is part of the meta source of the reduced graph. So let's peel that off. Okay. Yeah.
Wait, how did you know to also peel off what B was pointing to as B?
Well, I don't. I'm saying if I could, at this point, that's a fair question. If I could identify B and E were part of the meta source, I could peel it off. Now what's left? D has the highest one. And finally that one. So if I had a way to take the knowledge that this vertex is in a strong connected component and found all the others, I could peel off in this order. And it goes in order from the sources to the sinks. So what we're going to do now is reverse the graph and do a depth first search. Okay? So I want to find the strongly connected components of that graph. I'm going to reverse it and find it and do a depth first search. So we'll start at C and then D and then J, just because we got to do something. So and as we get post times, we're going to sort them in reverse order. So 1, that gets to 2, 3, 4. Okay, now we got to restart at D. Okay, so at that point we got the times. Now let's do it in descending order of post time. So we get that J is 24, and then L is 23, and so on. So we'll just go here at the end. And that is the lowest post time. Okay, what does this ordering tell us? What is it? Yes?
It tells you the first ones to start with, because they're gonna sync, and then you can remove them, and then the next one.
Okay. So this tells us that because J has the highest post time, that means that J occurs in a meta source of the reverse graph. But it also means that it occurs in a meta sink of the original graph. Yeah?
So do you explore from J to find the connected
Right.
components?
Right. So what we do is we go back to the original graph. We know J is part of a meta sink of that graph. So let's explore starting with J. So we did that original search on the reverse graph just to get an order to use to control another depth first search on the original graph. So it says start with J. So we start with J, take it off our list. And each time we visit something, we remove it from this list. So we see that one, that one, that one, that one, that one. And we're all done. We have identified a sink. Now, we don't have to physically remove it from the graph. Let's restart depth first search. It's nice now. It turns out that we do D. Turns out this order, we don't have to do anything about the ordering. This one is going to have the highest remaining post time, so we start there. Then we restart at C. So we're sort of peeling off the sinks. And finally we do A. So we reverse the graph, obtain this ordering, use that ordering to control the restarts of the depth first search over here. And each time that DFS calls explore, it finds a strongly connected component. Cool algorithm. Yeah?
Can you connect this to a real world application?
I'll show you a couple algorithms in a minute. Yeah?
So why are we peeling off sinks? Can't we just peel off the sources?
He's saying, why are we peeling off sinks? Why not peel off sources? Because we don't have a way. I don't know how to peel off sources. I know that if I start DFS in a sink, I will visit everything in the sink and stay there. In the meta sink, will stay there. The source doesn't have that property. You can escape from the source. You can't escape from the sink. So we just peel off the sinks and work back to the sources. Yeah?
Instead of reversing a graph to get your order, can we just go in reverse topological order to identify our...
You're saying reverse topological order, but this is not a DAG.
Great.
It's similar to a DAG algorithm in that we're reversing the graph and doing a depth first search to obtain some information that we then use in the next stage. But the next stage is another depth first search. So what's the complexity of this algorithm? Yeah?
V plus E plus V plus E?
It's just two, it said V plus E plus V plus E. It's two depth first searches. So the complexity is the same as that of the depth first search, which depends on what representation you're using. Okay? So just two depth first searches. Okay? This is, I really like this algorithm because it's in the end, it's pretty simple. It takes a while to sneak up on it. And it's the most complex PowerPoint animation I ever did. Yi Liang translated it into Google Slides yesterday. So, yes?
Is there a more efficient way where we only have to do one depth first search instead of two?
It's not the only algorithm. I think I've never learned there's it's named after someone whose name's escaping me right now. There's a competing algorithm I believe is more efficient than this. But.
Yeah, because you could just find the packages, right? It's a cycle and peel those off.
Well, yeah, I don't know if it's that simple, but there are other ways. They're not asymptotically any more complex, any less complex, but they're faster. Yeah.
So, I mean, this is cool, like you showed us how to do this, but how would we go about figuring out an algorithm like this ourselves?
Well, people made their name coming up with algorithms like this, back in the 70s. The people that invent new algorithms, they were intrigued in a class like this. They went to grad school. They did a PhD dissertation. They worked under an algorithm expert. They did a PhD dissertation, and as part of that, maybe they discover some new algorithmic ideas, and then they spend their life. That's their job, is investigating new algorithms. It's not easy by any means. People have breakthrough in mathematics, the same sort of breakthrough when people find new algorithms. All right, let's take a break and we'll look at a couple examples. showing the answers. Yeah, it still is. Oh, maybe. No. Okay. Forget that. Just take it away. Okay. So imagine a city where all the streets are one way. Imagine there's a city where all the streets go one direction. And the mayor claims that despite that fact, you can get anywhere in the city to anywhere else. Okay? How would you test that claim? Yeah?
See if every place in the city is part of the same strongly connected component.
Okay, you do strongly connected components algorithm, and if you can truly get from any place in the city to anywhere else, then the whole city ought to be a single strongly connected component. Right? Because that's the definition of a strongly connected component. Now imagine what you would be doing if you didn't know a strongly connected component algorithm. What would be another way you might test this claim? Yeah?
So if you have any node that doesn't have edges going into it, you know you can't go there.
Okay, yeah. You can certainly look for nodes that don't have edges, for sources. And what if there were no, it's not a DAG, so there may not be anything like that. Yeah?
I think the only way you could do it is with the quadratic algorithm.
Yeah, I mean, you could say, okay, for every vertex, I'm going to explore from that vertex and see if I reach everything else, something like that. You'd be inventing some algorithm, but once you know a strong component algorithm, you just say, well, I'll just run an SCC algorithm. So imagine you're on a job interview, and they're doing one of these programming problems, and they say, okay, they give you this. It's nice to be able to rattle off, that's, to recognize that's a strong component algorithm. Once you're educated in algorithms, that's always the hardest part, is taking a problem in the wild and recognizing, this is a majority voting application, or this is a strongly component algorithm. All right, now, I'm going to tweak that problem now. So it turns out that the mayor was lying, or maybe it was just wrong, that there is not a way to get anywhere from anywhere else. And so he makes a different claim. He says, well, at least anywhere you start, you can get to City Hall. Okay? So what?
Is that the map of the city?
No. This has nothing to do with the problem. Okay? So he's just claiming whatever the map of the city is, it's a directed graph. He's saying that anywhere you start, you can get to City Hall. All roads lead to City Hall. How would you test that? How can we view that? Yeah?
See City Hall as a source? Or sink?
A sink, right? Well, meta-sink. Would that work? So you take the graph of the city, you compute the strong components, and you check and see if City Hall is in a meta-sink. Yeah?
Other sinks wouldn't be able to make it there?
Right. If there's another sink, you wouldn't be able to get from this sink to from this meta-sink to this meta-sink where City Hall is. So how can we tighten up that test? Yeah?
It has to be the only sink.
Right. So you run a strong component algorithm, and you test whether you look at the meta vertices and you make sure there's only one sink, and if that sink contains City Hall. So if there's only one sink, then by definition, everything can reach it. Or if we want to know from City Hall, you can get anywhere. And you'd be looking for a unique meta source that contains City Hall. Okay. So I'll show you one more here. So we had remember the price and cost thing example I did on DAGs. So the idea was that you have a DAG, and every vertex has a price. So let's say the price is 2 or 5 or 6 or 1 or 8 or 10. And what was the cost? How was the cost of the vertex defined? Remember that? I did the lecture. So these,
Price versus cost.
so these things are prices. The cost was you determine the cost of vertex like C is defined as the highest price of any vertex reachable from C, including itself. So what would be the cost of C? 6. All right? And the price of F would be 5. So the question now I want you to now think about is, how can we make this into a graph? How can we solve this problem on a directed graph, not necessarily a DAG? So like what if we allowed cycles? Don't think about it for a second. I don't want an answer right away. And clearly it has something to do with strongly connected components. Yeah?
The price would be the highest cost of anything in the same strongly connected component? Or the cost would be the highest price.
Well, okay, let's just, since we know it has something to do with strongly connected components, let's draw them here. So there's one SCC, there's one, there's one, here's one, and here's one. So what often happens is you can take a DAG, you got some problem you want to solve on a DAG, turn the problem into a metagraph. I mean, not on a DAG. You want to solve a problem on a directed graph. Collapse it to a metagraph. Solve the problem on the meta vertices, and then solve the problem on the DAG. So what would you call the cost? How would you determine the cost of all the vertices in a strongly connected component?
Just the biggest one.
Just the biggest one. Because in a strongly connected component, each vertex is reachable from every other vertex. So they're all going to end up, well, I said the wrong word. What's the price of a meta? How do you determine the price of a meta vertex? And that's the largest price of anything in it. So this new meta vertex DE, we're going to say its price is 6. Now, how do you find the cost of every meta vertex? Okay?
It's like before, you just run the algorithm.
You just run the DAG algorithm, and it's going to decide that, okay, so this one is still 5, this one is still 6. Nothing's going to change because it didn't change the diagram much. And so whatever, so you determine all the costs, and then when you know that the cost of this chunk right here is 6, you know the cost of everything that it contains is 6. So it's, this isn't a very good example, this DAG here, this DAG wasn't this graph wasn't a very good example to start with. But the idea is, you chunk it into strongly connected components, you got a new DAG now, the price of each thing is the price of the largest thing that it contains, the price of each meta vertex is the price of the largest thing it contains. Then you determine the cost with the DAG algorithm. So a multi-phase algorithm that uses SCCs, yeah?
So is this a way to take a problem that you know how to model with a directed graph, but you don't necessarily know how to, like you're not envisioning how to model it with a DAG, so instead you turn the directed graph into like meta vertices and then process it as though it were a DAG?
Essentially, but it doesn't always work. You can't take any DAG, any directed graph problem you want to solve and turn it into a DAG problem. This one it works for.
So it might be something to consider, but maybe
yeah, it's just another trick you can use.
Okay.
I mean, let me try to draw a simpler graph here. So if we have like A, B, C, D, and then back to there, and our initial prices are like 5, 1, 2, 4. So we're going to determine the costs. And you can see from this that what's the cost of A going to be? That's going to be 5. What's the cost of B going to be? 4. The most expensive thing you can reach is 4. The cost of C will be 4 as well, and D. And the way that works out is we create that meta vertex, and its initial price of that meta vertex is just the largest of the prices it contains, so that's 5. And what will be the price of that meta vertex? 4, that's the largest one it contains. Now we run the algorithm, and we find out that the cost of this meta vertex is 4, and the cost of that one is 5. And we can turn it back into a solution to the original graph by just saying, okay, in the final analysis, the cost of A is 5, and the cost of B, C, and D is 4, which is what we expected to start with. Yeah?
So say like in that top graph, say C was maybe a group rather than one node, and a group of nodes, that was an strongly connected component. And then if the other one was say 7, and so you had to update, would you then have to go back and update all those individual nodes to 7?
So you want to put another vertex here,
Yeah.
and put this, and what price do you want to give X?
And so then maybe 7 for the next one over to the right. So that connected component will still be 6, but then the one to the right of it would be 7.
Well, putting an X here isn't going to change the thing over here.
No, but then when you had to compute the cost of that connected component, wouldn't you have to update it to 7 or to a higher one?
Well, you would compute the initial price of that connected component, be the larger of C and X's prices.
Right.
So I don't know, maybe that turns out to be 8 or something. Depends what X is.
Right, but what if the one, okay, so then you have your DAG, and then you're computing the cost. So I was assuming like that connected component with D and E, say it was 9 now.
Mm-hmm. But
So
what changed to make it 9?
Well, it was just
Okay.
nothing.
I'll
Well,
make-
one of the component, I mean something inside.
So I'll make that 9?
Yeah, so I guess what I was trying to, is then you'd have to update that other one to 9, and
Okay, so-
both of those then
Yeah.
inside of it?
I better talk to you after class because all this talk of the other one, and
Okay.
it's hard to follow.
Okay.
And my diagram's a huge mess right now. All right. That's not what I want there. Okay, now we're going to go on to a new topic. Breadth first search. I don't know why it's... What the heck's going on here?
Is your PowerPoint broken? It's in read-only mode too.
Okay, that's not... Try a different way of getting there.
That's a lot.
PowerPoint's angry.
All right, hopefully I can take the rest of the hour to do it. I could do it in here, but it's not gonna...
Well, there's a little maximize, right? On Canvas. They can go full screen.
Yeah, but we'll do the animations.
Have you tried unplugging it and plugging it back in?
Reset your router.
Thought process.
Okay. Work 4. Looking forward to my downloads here.
Oh, you never downloaded it, you just opened it.
Well, I've downloaded it before. All right, we'll try it. All right, well, I'll just do this. Okay. So, yeah, this is really unsatisfactory because of the multiple arrows. The idea is, we're talking about breadth first search trees here. So, when you search a graph, with depth first search, you end up with a tree, a search tree. So you do depth first search, you start at some vertex, and if you keep track of the order in which you follow edges, you end up with a tree. And then if the EFS calls another chunk, it gets its own trees. You end up with sort of a forest. End trees correspond to the end calls to explore. And a breadth-first search tree is also another kind of tree. It begins at a specific vertex and it finds the shortest path to every other vertex. But it still has a property that it's a tree. Now, what I wanted to show with this that I'm not able to because of the animation, I'm going to have to go to no.
No, that's, you have to scroll.
Yeah, this is starting to annoy me. Okay. All right. This is the idea. Suppose we have this. What's the shortest path from A to B?
A to B.
Okay, right there. The shortest path from A to C? Now let's say we found the shortest path from A to D. I guess I need to start with the graph with some edges in it. Okay, so the shortest path from A to B was this one right here. Right? The shortest path from A to C was this one right here. What's the shortest path from A to D? We need to go from A to B to D or A to C to D. So I'll just pick this one here. Let's say we go from A to B to D. Okay? Now, what's the shortest path from A to C to D to E? Or from A to E? We could go A, B, D, E, or A, C, D, E, right? So let's go this way, just for variety. That's why I had multiple edges on that graph. They were supposed to be animated. Now, there's a problem with, that's true, we found shortest paths, but what's the problem with the shortest paths that we used? Yeah?
The shortest path from A to E, it would be the same shortest path from A to D. So,
Well, no, the shortest path from A to E is of length 3, and there's the path A, C, D, E is the shortest. It's one of two shortest. But why would we prefer the path A, B, D, E over the path A, C, D, E? Yeah?
The shortest path from A to D is A, B, D.
Okay. So the shortest path we already found from A to D went via B. If we let the shortest path to E go through C, we can't encode all the paths as a tree. See, what we want is this. We want to start with A. We want to be able to describe, we want to be able to construct a shortest paths tree. So these are our original edges. And what we want is to go here, to go here, our shortest path from A to B, to share the shortest path from A to B, and then the shortest path from A to E, share, share, share. And then if we ignore the edges that we didn't take, no. If we ignore the edge we didn't take, we end up with a tree. That's a breadth first search tree. So the whole point of that demonstration is we want to be sure that that when we describe, when we're picking the shortest paths from a start place to all the other vertices, that we can describe everything as a tree. So it better not be the case that you get from A to B, you go A to B to D, but then the shortest path to E doesn't involve going through D. We want to avoid that. Okay, so that's what that says. Okay, so that's showing you in color. The shortest path from A to every other vertex. This is a situation where, whoops, this is what we want. This is the shortest path tree that encodes how to get from A to E. Now, once you can do that, you can encode the information in this tree in a couple of arrays. So this is the previous array, and it says, well, what information is the previous array telling us? How is this tree right here? How is this purple tree encoded into the previous array? Go ahead.
It's what node you just came from when you're standing on it.
Okay, so this is saying that in this tree, what's the predecessor of B? A. And so that's what this says. You look in the previous of B and it tells you which vertex came before it in the shortest path tree. There is no vertex before A. The vertex before E was D, so you look in previous of E, you see D. And F, there's no way to get from A to F. So unlike depth first search, when we do breadth first search, we don't restart the search. We start at a vertex, we find all the places we can reach, we're done. If it's unreachable, so be it. The distance array just says how many edges it takes to get from one to the other. So that's all that information, and F is infinite because there's no way to get to F from A. All right, this is the algorithm. And people have mentioned this. I imagine you've seen this before. But I'll give you the 2-minute version. We'll revisit this next time. What this does is it initializes the distance in previous arrays to infinite and null. So it marks it stores a null everywhere in the previous array and an infinite everywhere in the distance array. Then it sets distance of S, the starting vertex, to 0. And up there, that entry next to A ought to be 0 in that distance array. Okay? It creates a queue and sticks S on it. And essentially, it just loops on the queue. It pulls out an element from the queue. It finds all the edges out of it. If the node distance to that vertex is infinity, why would that be interesting? Why do we only care about, we see there's an edge, we just pulled U off the queue, so we're trying to grow the tree. We find out that U, there's an edge from U to V. We check to see if the distance to V is infinity. Why is that interesting? Yeah.
It hasn't been visited yet.
It means it hasn't been visited. So we throw it on the queue. The distance to U is one more, and the distance to V is one more than the distance to U was, because it took one more edge. And the previous of V is now U. And since we're using a queue, the ones that have been on the queue the longest have the, come off first. And so that's what makes it breadth first, rather than depth first. Okay? So, this is an animation. I think what I'm having is an internet problem, actually. So, we'll stop there and start up again next time.